Hi, my name is Eleni, and in this talk I'll present our paper towards resilient data management for the Internet of Moving Things. This is joint work with Elena Uro and Volker Markel. I am quite certain that many of you are watching this video right now from a mobile device. Smartphones, tablets, smartwatches, and other wearables have become ubiquitous, and their presence in our lives has been forecasted to increase in the next few years. This trend, combined with their ever-growing computing capabilities, makes them really attractive for Internet of Things applications, where mobile devices can be used to both generate data and to process it. However, supporting IoT applications over mobile devices is very challenging, mainly because mobile devices are continuously changing their position within the network, and also because they are prone to transient disconnections caused by network instabilities. Previous work on stream processing uses mainly different flavors of checkpointing and replication for fault tolerance. However, both of these approaches are based on the assumption that data sources can be replicated. That is, when a data source loses connection, there is always a backup data source available that can take its place. In reality, that is not always possible. Furthermore, both fault tolerance approaches fail to leverage the computing capabilities of the offline devices. Just because the device is disconnected, it does not mean that it stops generating and processing data. What we are proposing is a reactive, buffering-based fault tolerance strategy, specifically tailored for mobile data sources. We integrated our strategy with Nebula Stream, which is a novel general-purpose data management system for the Internet of Things, currently under development by our group DIMA at TU Berlin. At a very high level, our strategy works as follows. When a disconnection occurs, we take an optimistic approach. That is, we always assume at first that the disconnection is transient and we wait a certain amount of time for the device to rejoin the network. If time runs out and the device hasn't joined back, only then we assume that it will never return, and we can default to other fault tolerance strategies that handle permanent disconnections. When we do have a transient disconnection, we let the device continue generating and processing data, and we buffer the processed data so that we can send it after the connection has been regained. At reconnection, because our devices are mobile, it is possible that they will reappear at a different point in the network. To deal with this, we use a combination of selective redeployment and auxiliary forwarding queries, which I will explain in more details later in the talk. But first, let's look at the buffering strategy and what happens during the transient disconnection. So as I said, our devices, which are acting as data sources, continue to generate and process data during the disconnection, and we want to buffer this data. To minimize latency and optimize the use of the device's space, we employ a circular buffer. Circular buffers are particularly suited for applications where we want to retrieve our data in a first-in, first-out fashion. Our buffer stores batches of data for all the different queries that our data source is involved in. Because for every different query, we might be generating tuples of different sizes, and each of the batches may have a different number of tuples. Instead of just adding this data directly to our buffer, we always proceed it with a control block, which indicates the query that this batch belongs to, the tuple size, and the number of tuples in the batch. Additionally, because there are so many IoT applications and there are so many different kinds of mobile devices, we give the user the possibility to choose the best buffer size for each application and device. Users can decide the buffer size for a particular device based on things such as the device storage capacity, the data generation rate, the expected disconnection time, or any other application-specific knowledge that they may have. Now, what if our device has been disconnected for a little bit too long and our buffer fills up? At this point, we need a policy that enables us to decide which data should remain in the buffer and which data will be discarded. In this work, we use two approaches. The first one is a very simple and straightforward first-in, first-out replacement policy, where we discard the oldest batches from the buffer to make space. Our second approach, which is a little bit more sophisticated, is called query-aware FIFO. The goal of this approach is to keep at least some data for each of the queries that the source is involved in. So whenever possible, if we receive a batch from a particular query and the buffer is full, we will look for all the batches of that same query and start removing them from oldest to newest. If we do not have any batches for that particular query in the buffer, or there are some, but after removing all of them, we still not have enough space for the new batch, then we start removing the oldest batches of the query that has the highest number of batches stored in the buffer. This means that we are not simply removing data in a sequential order, like in the simple FIFO approach. We might pick a batch from anywhere in the buffer, which can cause segmentation. To avoid this, what we do is that whenever we remove a batch from the buffer, we shift up all the batches that are stored after it to cover all the empty space. This is basically all that we do while the device is disconnected. Once the device regains connection, it sends a notification to the coordinator of the system. This notification says, "Hey, I am back." In addition, it includes information about the list of queries that the device is involved in, and also about the current immediate neighborhood of the device. That is, what are the nodes in the network that the device can directly connect to. With this information, the coordinator will determine for each of the queries what to do next. We have two possible scenarios. In the first scenario, our device has not moved at all, or it has moved, but it can still reach the node to which it was sending data before the disconnection. In this case, we can simply resume query execution. We take the data from our buffer and we send it to the next upstream node. Otherwise, if the device has moved out of the upstream node's range, then we need to redeploy our query to find a new path. When we redeploy a query, the source and the sink of the query do not change. The source is always tied to the mobile device, as it's the one generating the data, and the sink node, where the fully processed data goes at the end, also remains the same. What can change is the path that joins these two nodes, and also the operations of the query that are assigned to each node in the path. We determine three different scenarios based on which operators are assigned to our source. The first one is the simplest. The source is assigned exactly the same operators as before the redeployment. In this case, the source has completely processed the data in the buffer with respect to the new deployment, so the source does not need to do anything else with the data. We can simply remove it from our buffer and send it to the upstream node indicated by the new deployment. In the second scenario, the source has been assigned a superset of the operators it had before. In this case, not all of the operators have been applied to the data in our buffer. So we simply take the data from our buffer, we apply the additional operators, and then send the data to the upstream node. The last scenario is the most tricky one. This is when our source has been assigned a subset of the operators it had before. In this case, if we were to send the data directly from the buffer to the next upstream node, we would be applying some operators to the data twice. To address this problem, we use a mechanism that we call forwarding queries, which I will explain now with an example. Here is a topology where worker 4 is the source. It generates the data and also applies a filter operator over it. Then it sends the data over to worker 1, which does not perform any transformations. It simply forwards the data to worker 0, which is our sink. Imagine now that worker 4 loses connection. After being disconnected for some time, it rejoins the network in a different position. Now it has moved out of workers 1 range, and it can no longer communicate with it. As a result, the coordinator decides to redeploy our query. This is the new assignment of operators that we get. If we just take the buffer data from worker 4 and send it to worker 3, we would be unnecessarily filtering the data again. Instead, we just want to send this data that is already fully processed to the sink node. To achieve that, we generate a forwarding query. A forwarding query, as its name implies, is essentially a query that does not perform any transformations over the data. It simply contains a series of forwarding operators that bring the data from the buffer to whichever operator needs to be applied over it next. So overall, we have two paths. Any data that is generated after the disconnection follows the blue path, and the buffer data is sent through the green path. Once all the buffer data reaches its final destination, our system is back to normal, recovery is complete, and we can remove the forwarding query. Let's now move on to our experimental evaluation. In our experiments, we used a scenario that is quite similar to the example I just showed. We had a source that was running two queries. One of them was using a CSV file to simulate data generation, generating data at a rate of 3.33 megabytes per second. The other one was using a binary generator, generating data at a rate of 488 kilobytes per second. Each of these two queries was applying two filter operators to the data, besides the source and the sync operators. The goal of our evaluation was to compare our strategy with the baseline nebula stream. This baseline uses a pessimistic approach to disconnections. It assumes that if a node leaves the network, it has left for good. So if the node rejoins later on, it is treated as an entirely new node, and the queries that it was participating in have to be deployed again from scratch. The first experiment measures the data loss ratio. Usually, in real-world scenarios, we don't have control over our data source, so we cannot simply pause it when it is disconnected. This means that if we do not do anything, by default, all the data that is generated during a transient disconnection will be lost. This is the case for the baseline nebula stream. Since it assumes that the node is gone, it ignores any data that it might be generating, and we are losing it. So we wanted to measure the percentage of lost data with respect to the duration of the disconnection. In the plot, we draw the baseline with blue color, and our strategy denoted as NES MSS with red and maroon color, depending on the replacement algorithm. As you can see in this plot, the baseline always loses all data. Using our strategy, we can completely eliminate data loss when the disconnection is short. When we get to the point, in this case 15 seconds, where the disconnection is long enough for the buffer to become full, then our replacement strategies kick in and we start discarding data from our buffer. In this case, you can see that the query-aware strategy performs better than the simple FIFO one, and this is because one of our two queries is generating significantly larger batches of data. So whenever we are using the standard FIFO for storing a small new batch, and the oldest batch that we are removing is a larger one, then we are losing more data than what we are gaining in a way. In contrast, the query-aware FIFO prioritizes the removal of batches of the same query, so we are more likely to eliminate a batch that is similar in size to the one we are adding. This is, of course, application dependent, and our idea is to allow the user to choose the replacement strategy that fits better her purposes. We also compared our strategy with baseline NES with respect to the query runtime. We wanted to see if our selective redeployment approach reduces the overall query execution time. In this experiment, we are running just a single query. The graph on the left-hand side compares our approach, NES MSS, with the baseline NES in a scenario where there is no mobility during the disconnection. On the x-axis, we vary the number of disconnections, and we measure the runtime in seconds on the y-axis. Since there is no mobility, our approach does not redeploy the query. However, the baseline NES treats the node as new after each disconnection and redeploys the query again and again when the node returns. As a result, as the number of disconnections increases, the runtime for the baseline NES grows. In contrast, using our strategy, the runtime is not affected by the number of disconnections, assuming also, of course, that each disconnection has a negligible duration. However, since we are using mobile devices, often the devices will move during the disconnection. To see the impact of mobility, let's look now at the plot on the right-hand side. Here, given a certain amount of disconnections that occur during query execution, we increase on the x-axis the percentage of those that require redeployment. On the y-axis, we measure again the query runtime in seconds. As you can see, in the best case scenario, When no redeployment is required, we are much faster than the baseline, and in the worst-case scenario, when the device moves in every disconnection and query redeployment is always required, then we perform just the same as the baseline. This means that even if we have just one disconnection that doesn't involve mobility, our selective redeployment approach will already bring some benefits. In real-world applications, we expect to see a mix of different types of disconnections, some with and some without mobility. To summarize what we talked about in this video, we proposed a reactive, buffer-based fault tolerance strategy that seeks to mitigate the impact of transient disconnections of mobile data sources. Our strategy exploits the offline computing capabilities of the data sources by allowing them to continue generating and processing data during transient disconnections and storing this data in a circular buffer. If there is mobility during the disconnections, we handle it using two mechanisms. With selective query redeployment, we redeploy the query only when the device moves out of range of its upstream node. Furthermore, with forwarding queries, we send the buffer data through a different path than the one indicated by the new query plan to avoid redundant processing. Compared to the baseline Nebula stream, our strategy achieves a reduction in data loss, particularly for short tangent disconnections, and it also reduces query runtime by avoiding query redeployment when possible. This concludes my talk. Thank you for watching.